Well, this video is for section 2.2 of Math 112, and this starts on page 57. And I think it's really helpful to look at these first couple pages, okay? So I'm going to talk mainly about the ending points of this, which is a graph of the sine function. Draw a little sketch of that. So there are some important parts of the graph I'll talk about more in just a second. So when we were talking about the values of the sine and cosine in section 2.1, I talked about how at the quadrantal angles, those values can be 0 or positive or negative 1. So let's see, I'm going to draw the sine function here. 1, 0, 0, 1, negative 1, 0, 0, negative 1. The cosine is the x-coordinate. The sine is the y-coordinate. So the sine of 0 is 0. At pi over 2, which is 90 degrees, the sine of pi over 2 is positive 1. Over here, at pi radians, 180 degrees, the sine of pi is 0. That's the y-coordinate. And then down here at 270, which is 3 pi over 2 radians, the sine of 3 pi over 2 is negative 1. Again, the y-coordinate. And then when we come back, these things just repeat. Okay? So there will be another curve that looks just like this one. We'll do some more with applications of these ideas. They're really useful for periodic phenomena. One of my favorite applications is the length of day, which is a periodic phenomenon that follows the type of graph that a trigonometric function is. And it makes, I think, for some really interesting ideas in what's happening to the length of day. And how much sunlight we get at different times of the year. Okay, so in any event, in the textbook, I kind of fill in the spots between these points. Okay? So I'm not going to do that here. I'll just put the quadrantal values up there and then connect them with a curve, and that's one period of the graph. Okay, we get one full period from 0 to 360, and this is the graph of y equals sine theta, or if we put theta on the x-axis and y on the y-axis. Okay. All right, so that's the fundamental idea. Cosine is going to look a little bit different because we're going to be working off of these values. Cosine is going to start up at 1. And I always chop this up into 4 pieces because these quadrantal angles have these special values. You get 0, maximum, 0, minimum, and back to 0. Okay? So it's important to identify these y values with these x values. Okay? So once we know the length of the period, then we can chop that up into 4 pieces. This will be half of that. This will be half of this. And then this one will be these two added together. 3 pi over 2. So again, the cosine starts at 1, then goes to 0, and then to negative 1, and then back to 0. So it goes maximum 0, minimum 0, maximum. Maximum 0, minimum 0, maximum. And that curve will look like this. Now they look different, right, within this range of x values right here, but they're really the same. Like if you match this up with this piece over here, you can see that it's really just been shifted, what is it, by pi over 2 radians. Okay, and that's a fundamental idea about sines and cosines. They have the same shape, but they're offset along the x-axis. Okay, let's see what else we want to talk about here. So that's the fundamental idea for sines and cosines. All right, let's label this one. Y equals cosine theta, where this is theta, and this is y. All right, so there's the fundamental sine graph, the fundamental cosine graph. Now that we've established those, now we're going to play around with them, okay? All right, I'm going to erase these, but they're still in the textbook, and they're good to have for reference. And again, these maximum and minimum and zero values, these come from these quadrantal angle values for sine and cosine. All right, let's see. I'll leave the sine graph up there. And then let's consider what if we had a graph that said, oh, y equals 3 sine theta. Well, what would happen is that all of those, we would find the value of sine theta, and then we would have to multiply it by 3. So instead of the maximum being 1, the maximum would be up at 3. 1, 2, 3, there's that. And then the minimum would be down at -3. There's our period of 2 pi, split it into 4 pieces. And then we start at the 0, go up to the maximum, back to 0, down to the minimum, back to 0. And there's our sine function for y equals 3 sine theta. Okay? So this coefficient right here is called the amplitude. And so that tells you how tall, big, or small your wave height will be. Okay? All right. So that's the amplitude. Now let's talk about the period. So the standard period for the sine and cosine functions is 2 pi. All right? Now, if we put in a coefficient, not on the outside, but inside the sine function, the sine of 2 theta, and I think I do this example in the textbook as well, what happens here, now the amplitude is going to go back to being +1 and -1, okay? But this is going to affect the period of the function, because now, when theta is pi, we're going to multiply that by 2 and then find the sine of 2 pi. Okay? So this thing, this value right here, which was over at 2 pi, is actually now going to be over here at pi. So what that says is that this is our new period, is pi. So we're going to chop this up into 4 pieces, pi over 4, pi over 2, 3 pi over 4 pi, and then we're going to go 0, maximum, 0, minimum, back to 0. We could do another set here to get out to 2 pi, but in most of these problems, I'm just asking you for 1 period. Okay? All right. So the reason for that is, right, is because if theta is pi over 4, we multiply it by 2. That makes pi over 2. And then we find the sine of pi over 2. That's the maximum value of 1. That's why this maximum value is happening at pi over 4, is because that's getting multiplied by 2 before we find the sine. All right? So, in general, the amplitude, let's see. If we write this as y equals a sine, let's see, I think in the textbook it said a sine of b theta. Where do I put that? Yeah. Yeah, page 64. A sine B, and I think I'm using x in the textbook rather than theta. And that's fine. There's nothing wrong with that. This is our standard equation, whether it's the sine or the cosine, right? Their shape will be a little bit different because they're offset, well, their shape will be the same, but they'll be offset along the x-axis. And in this case, the amplitude is defined as the absolute value of this coefficient, amplitude, and then the period, right? Normal period is 2 pi. If we put a 2 in there, the period goes down to pi, so we're going to take 2 pi divided by whatever that coefficient b is. That'll tell us what the period is. Okay, so there's the basic information for section 2.2. I think we're ready to do some examples here. I didn't talk about having a negative amplitude, but I think we'll see that as I go through some problems. What that's going to do is it's going to start you off and go in the opposite direction. Okay. So, well, here's the very first example we've got here. Problem 2 has a negative amplitude. Y equals negative sine of 2x. Okay. So, remember the standard sine function looks like that. Okay? This is y equals sine x with a period of 2 pi and an amplitude of 1. All right. So, what we want to do, if this is a negative sign, right, when we find the sine of this value, it would give us a value of positive 1. This will turn that into negative 1. So instead of going to the maximum first, it's going to be going to the minimum first. So first off, there's the period. Split it into 4 pieces. I'll talk about what the period is in a minute. But first off, we're going to start at 0, go down to the minimum, back to 0, back up to the maximum, and back down to the 0. Okay? So this is what a negative amplitude does to the sine curve, is it flips it around. Okay? Now, the period here is going to be 2 pi over 2, which is pi. So there's our period. So then when we split this up into 4 pieces, this will be pi over 2, half of that. This one will be half of this one, pi over 4. And then this one will be 1 pi over 4, 2 pi over 4, 3 pi over 4, and 4 pi over 4. Okay? That's one way to get used to doing this, is to get the period, cut it in half again, and then start counting. 1 of these, 2 of these, 3 of these, 4 of these. Okay? All right. So that's problem 2. Let's see if I left anything out there. Determine the amplitude in the period and graph one period of the function. Okay. So let's see here. The amplitude here was 1. All right. And so this is the period. Amplitude is the absolute value of whatever this is, and so we define that as just being 1. Okay. All right. Let's look at some more of these. Problem 4, we're interested in -2 cosine 5x. All right. So again, we'll draw a little sketch of our standard cosine function. So the standard cosine function is going to look like that. Now this is going to give it an amplitude of 2, so the maximum value will be positive 2, the minimum value will be negative 2. But this negative here means that it's going to start down at the minimum value. So there's 2, there's negative 2. And so this graph is going to start down at the minimum because this is negative. And then I'll put the period on here. I'll label these in a minute, but we're going to go first to the 0, then maximum, then 0, and then minimum again. And so our graph is going to look something like that, right? Which is this thing flipped upside down with these maximum and minimums doubled because of this 2 right here. All right. Now the period, right, is 2 pi divided by that coefficient b. So that's 2 pi divided by 5. All right? So that's going to be our label right here, 2 pi over 5. If you prefer decimals and you want to call this 0.4 pi, that's fine. This one's easy. It's a terminating decimal. If it's a repeating decimal, then you're going to need to use bars over your repeating decimals. Okay, so remember how to do this. Cut this in half, that's 1 pi over 5. Cut it in half again, that's pi over 10. So this is 1 pi over 10, 2 pi over 10, 3 pi over 10, and 4 pi over 10. Okay? And that's it. You know, the assignment says to identify important values on the x and y axes, but we've done that by identifying these and identifying these, right? So this is pi over 10, 0, this is pi over 5, 2, and so on. You don't necessarily have to label the points, but you do have to label your axes in a way that we can see what the points are. All right, that's problem 4. Let's keep going. Problem 6. Y equals 2 sine 1/3 x. Okay? So again, here's your standard sine function. And so we're going to work off of that. Here, our amplitude in this case is 2. Here's our period. We don't necessarily know what it's going to be yet, but we know the sine function is going to start here, go up to 2, back to 0, down to negative 2, and back to 0. So it'll look something like that. Okay? And our amplitude here is equal to 2, and since it's a positive 2, it goes up first rather than down first. All right, now the period is 2 pi divided by 1/3. All right? That means that you have to multiply by the reciprocal. This is 2 pi times 3 over 1, which is 6 pi. The smaller this coefficient b is, the more stretched out and the larger your period will be. Okay? The larger this number is, the more compressed your period will be. So this is going to be 6 pi out here. Cut it in half to get this value, which is 3 pi, and then cut it in half again to get 3 pi over 2. So 3 pi over 2, 6 pi over 2, 9 pi over 2, and 12 pi over 2. Right? I'm just counting because each of these distances is going to be 3 pi over 2, and so it goes 3, 6, 9, 12 pi over 2. All right. Look at a couple more of these before we switch it up and try to write an equation based on a graph. Okay, let's look at problem 8. This is, let's do problem 12, because we've already seen a negative cosine, so let's do a positive cosine. 12y equals 3 cosine 5/3, not pi, 5/3 x. Okay. So, again, let's look at the standard cosine graph. It's going to be looking something like that. Okay. So here, our amplitude now is 3. Okay. Let's see. We'll worry about the period later. You can do the period first if you want. You can label these first. There's nothing wrong with that. I just like to get the sketch done based on the amplitude. So we're going to start up at the maximum, which is positive 3, and then go down to 0, minimum, 0, maximum. Draw our little sketch, and so it's going to look like that. Okay, standard cosine graph with a amplitude of 3. So our period here is going to be 2 pi divided by 5/3. So that's 2 pi times 3/5, which is 6 pi over 5. All right, so that's this point right here, 6 pi over 5. Half of that is 3 pi over 5, right? And then, to cut this in half, you double the denominator. This is 3 pi over 10. So we go 3 pi over 10, 6 pi over 10, 9 pi over 10, and then 12 pi over 10, reducing, of course, each time. But if you don't reduce, then it's easier to keep track of where you're headed to, okay? All right, let's see here. So that's it for number 12, all right? So let's move on to the second half of the assignment. This is where we're going to build an equation based on a graph. Let's take a look at those. All right, problem 14. So here's our amplitude is going to be 2, and then this is pi over 2, pi over 4, pi over 8, 3 pi over 8, and this is a standard sine curve. Okay. Well, let's see here. So, we know that this is a sine curve because it starts at 0, goes up to maximum 0, minimum 0. Alright? So y equals a sine bx. Well, the a is going to be 2, right? It's an amplitude of positive 2 because it goes up first. 2 sine bx. Well, the b is related to the period. So 2 pi over b is equal to pi over, not pi over 8, pi over 2. Pi over 2. Now you can do a variety of things to solve this for b. You can take reciprocals and multiply on both sides by 2 pi. You can cross multiply and get b pi equals 4 pi. So b equals 4. Okay? That's the way I'm going to go about doing it, because now we're done. This says y equals 2 sine 4x. There we go. Okay? So, you can pick the amplitude from the maximum and minimum values, and whether they go to the maximum first or whether they go to the maximum second, because that's going to tell you whether this amplitude is going to have a positive or negative sign to begin with. And then to find the value of b, just put the period in here and solve for b. All right? All right, let's look at a couple more of these, and then we'll finish things up for section 2.2. All right, problem 16. Let's see here. Got an amplitude of 3. Let's see, a period of 4 pi. There we go. Oops. Okay, so let's see here. Well, this is a cosine graph, right? Because it starts at the maximum value. So, it would be A cosine Bx. The A is going to be a positive 3, right? Because it starts at the maximum value. If it started down here, we would put a negative 3 in front of it. All right? And then the value of B, oh, I didn't erase this part. So, let's see here. 2 pi over b equals 4 pi. Let's see, what are we going to do here? Let's multiply on both sides by b. And then divide on both sides by 4 pi. B is a half. And there we go. Y is 3 cosine a half x. Okay. Well, that's problem 16. And again, if you want to, look at these for longer than I leave them up on the board, then by all means, stop the video and rewind it and so on. In class, I would stand in front of it for a minute or so and check and make sure that everybody's got it before I erase it and move on. Okay, let's see. Problem 18. What do we have here? We've got max and minimum values at 1.5. And then we've got this period of 5 pi. 5 pi over 2, 5 pi over 4. And so this will be 5 pi over 4, 10 pi over 4, 15 pi over 4, and 20 pi over 4. I mean, they're labeled, but sometimes it can be helpful to practice that. And this one, we start at the minimum, go to 0, up to the maximum, back to 0, and back to the minimum. This is a negative cosine function. Because remember, your standard cosine looks like this, right? So if this is starting out down at the minimum value, that's saying that the A is going to have to be negative. Negative 1.5 cosine, and then our period is 5 pi. So we say 2 pi over b equals 5 pi. So b is 2 pi over 5 pi, 2/5, 4.4, whatever you prefer, but there it is. Negative 1.5 cosine 2/5 x. All right, let's look at one more of these, and then that'll be it for section 2.2.